Sometimes recurrent relationships are not solvable. They are too complicated, they have too many terms. In this case, we can solve it. If we know an plus 2 is defined, it's resolved as minus an divided n plus 1 times n plus 2. So for every n positive, if we know an, we can construct an plus 2. It's also a particular recurrent relationship. There is no an plus 1 in this relationship. That means that every time you're computing something, you are referring to something that is two terms before in your series. So if you're thinking of the sequence A0, A1, A2, and so forth, every time you're picking an even term, it only depends on the previous even term. If you're picking an odd term, it only depends on the previous odd term. And you can keep jumping earlier and earlier in the sequence until the starting points are A0 and A1. Let's try to look at this a bit more. If we have A0, then we know that A2 is equal to minus A0 divided by 2. Then we know that A4 is equal to minus A2 divided 4 times 3. But A2 was already well defined, so if you do the calculations, it is A0 divided 4 factorial. A6 only depends on A4, so A6 is defined as minus A4 divided 6 times 5. And because we know A4, A6 is minus A0 divided 6 factorial. And we keep on going on, and we never need to use the odd terms. So all the even terms only depend on A0 at the end of the day. In general, if we want to write n equals to 2k, the even term a index 2k, if you check the pattern that we're following, a at the index 2k is equal to minus 1 at the power k divided 2k factorial, all of this multiplied by a0. And you can do the same approach to look at odd terms, so terms that are in the shape a at the index 2k, even, plus 1, odd. And that term has the shape minus 1 at the power k divided 2k plus 1 factorial, all of this multiplied by a1. This has a pattern we were discussing. All even terms all only depend if you go down in the sequence on a0, and all odd terms depend if you go down in the sequence on a1. So we can write it down. We can write yx as the sum of a0 plus a1x plus minus a0 divided 2 factorial x squared plus minus a1 divided 3 factorial 3x to the power 3, and so forth. And we divide this by trying to divide the terms that depend on a0 and the terms that depend on a1. That we can do because of how they are constructed. So a0 is multiplied by this sequence that is 1 minus x squared divided 2 factorial plus x to the 4th divided by 4 factorial minus x to the 6th divided by 6 factorial, and so on. You see the sign is shifting at every round. We're jumping powers of x 2 by 2. And at the bottom you have the factorial of the index of the power of x. A1 is multiplied by something similar, but shifted in a certain sense. We start at x, and then we have minus x to the 3rd divided by 3 factorial, plus x to the 5th divided by 5 factorial, minus x to the 7th divided by 7 factorial, and so on. Both of these terms we have seen before have a specific pattern, so we can write both of them as infinite series. With the formulas we used before, we can write this down. So we have a power series for the terms that are multiplied by a0, and a power series for the terms that are multiplied by a1, and they are completely disjunct. The 1 multiplied by a0 is a sum from k going to 0 to infinity of minus 1 at the power k divided 2k factorial x at the power 2k. And the power series multiplied by a1 is sum from k going from 0 to infinity of minus 1 at the power k divided 2k plus 1 factorial multiplied by x at the power 2k plus 1. Now this is not the usual shape for power series, because what we were talking about before, we usually want the index of the power series to be the power of x. Well, in this case, the index is k and the power of x is either 2k or 2k plus 1. So it's not the format for power series we usually like. But we stick with this because both of these power series are very important basic trigonometric functions. You might know them. If you don't know them, I advise you to look at them very sternly, because we are going to be using sine and cosine quite often every time we're going to look at power series. And either way, the cosine is the power series of all even powers of x, and the sine is the power series of all odd power of x. Each time, each new term has this switching sign with respect to the previous one. So we have retrieved, through the use of power series, the information we already knew in a certain sense. We have retrieved that the fundamental set of solutions for our initial ODE is sine and cosine. But we have built it in another way. We have used a different path to get there. I just want to look at a reminder. We have talked at the beginning about the fact that things work only if we're working in the interval of convergence of the power series we're looking at. So just a reminder, if you're looking at a power series around x0, on what interval does it converge? Well, there is this convenient theorem that states that if you're looking at a sequence of coefficients of a power series, if you compute the limit of the absolute value of the next coefficient with respect to the previous, so n plus 1 divided by n, if you look at that limit, and that has a value L, the power series converges on the interval x0 plus or minus 1 divided by L. It diverges out of that interval. So from minus infinity to x0 minus 1 over L, and from x0 plus 1 over L to plus infinity. So we have an interval in which we know things work properly, and we have two intervals in which we know things don't work. You might have noticed that all these three intervals have round parentheses around. That means that all these intervals do not include the boundaries. So because they don't include the boundary, what does it mean for the boundary itself? So what is happening at x0 minus 1 over L and x0 plus 1 over L? Unfortunately, there is no easy theorem for that. You have to plug in that value in the power series. It becomes a series, and you have to compute it and see if it converges or not. This theorem only tells you things about the intervals that do not include the boundaries. So unless you do some extra study, you don't know what is happening exactly at x0 minus 1 over L or x0 plus 1 over L. You know everything that happens on either side of it. And that's usually enough to understand what is going on. So applying this theorem, we ask ourselves, where does our power series that correspond to the cosine, where does it converge? So we're going to just apply the theorem. The theorem asks us to compute the limit for n tending to infinity of the absolute value of an plus 1 divided by an. So we compute this limit. This is minus 1 at the power k plus 1 divided to k plus 1 factorial. All of this divided by minus 1 at the power k divided to k factorial. And we simplify things, and this is equal to 0. So it converges on the interval 0 minus 1 over 0, 0 plus 1 over 0. And that tends to plus and minus infinity. So it converges over the whole interval. In general, what does it take to solve for power series? First of all, you want to find an ordinary point. Then you want to write the solution as a power series. So you want to write it in the form sum from n equal to 0 to infinity of a n x to the power n, or x minus x0 at the power n. Then you want to find a recursive relationship for a n. What does it mean? It means that you want to find a formula that determines a n plus something with respect to a n. You want to disentangle the solution into a fundamental set of solutions. What does that mean? It means that you want to unwind the recursive relationship in such a way that you can detect which parts depend on what. Once you have the fundamental set of solutions, then you proceed as normal. Disentangle the solutions into a fundamental set of solutions is sometimes hard, if not impossible. So instead, you want to consider that the information on the initial conditions, so on y and on y prime at the initial value of t, give you information about a0 and a1. That means that if you have found a recursive relation that indicates a n plus 1 plus 2 depending on a n plus 1 and a0 and a n, if you have a0 and a1, you can actually start computing this recursive relationship. You might not be able to fully understand the fundamental set of solutions explicitly as we did in the example, but you're still able to compute the special solution for a given initial condition.